Okay. I guess we are recording. 1 second. Okay. So we'll start. Hello all, and welcome to the week 4 live session of your course Introduction to Machine Learning. My name is Raj, and I'm a PhD student in IISc, and I'm a PMRFTA. And today's agenda is going to be, we'll solve previous week's questions. So one thing which came out in the past session with, I guess, Sudeep, was that some of you requested that you want to have a session on how to solve problems, especially. So I'll be handling that session for today. um, and as usual, like, we are currently recording this session, so whatever is there will be made available later on, and also anything that I write here will be made available in a PDF format. All right. um, okay, so we'll go through previous week's questions in reverse order. um, so we'll start with, so I haven't written taken down questions here. Rather, can you guys see the screen where I have opened up the week 3 assignment?
Yes, sir. Yes.
Okay, good enough. So we'll go one by one, and in case you have something that you want to discuss or see, we will start from there. Yeah. Uh, okay. So week 3 questions. Do you guys have any specific doubts as such, or anything which is very difficult here?
Can you ask one question that is regarding assignment two?
Assignment 2,
Sir,
you
in
said.
question assignment 3, there some lines are given orange, red, blue. Can you
No,
just
no.
explain that first?
Okay, this one, right? Yeah. Okay. So what is the question here, right? So we have some classes, plus and minuses here, right? And you have some lines drawn here. So the question is, performing LDA on which line is the most appropriate for projecting data points, right? So what do you think should be the answer, and why should it be that way? Any ideas? Anybody want to take a guess at it? No.
I answered as orange
Uh-huh.
as it's separating the two classes, but it's
Hmm.
actually wrong. So I didn't
Right.
exactly understood the part. What exact logic is required here?
Yeah. So what is the question, right? The question is, like, we want to know which line is it the most appropriate for projecting the data points. So as we know, in LDA, the idea is that, let's say, if I have some points here and some points here, let's say plus and the negative class, what you will ideally do is you will project it on some line here, right? And then have like a threshold sort of a thing to separate these two classes of data, right? So in the question that is there, this is the orange line. So orange line is the line which separates the data. That is correct, right? But the question is, you want to know which line is it appropriate to project them. So if you project in on this line, you can actually get them in a linearly separable method, system, right? Because then you can just have a threshold value of this value, and you can say whatever is more than this or less than this, and therefore this could be the line on which you can project the data.
Okay.
Okay, so this is the projection line that you should ideally use, right? So okay, let's just name it. So this is week 3 quiz we're solving, and this is question number 9. Okay, all right. So that's the reasoning for it being blue as the answer. Yeah. Okay.
Hello, sir.
Yeah.
Sir, would you just to please explain that above that one, sir, that which we have to classify the data set will mean. I'm little bit doubt, sir, in that. So just to give brief idea, sir.
These two,
That one, sir.
7 and 8.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay, right. So the idea in 7 and 8 is that so you need to see exactly what the mean and variance values are, right? So let's go for so question 7. Question 7, we have means is, so this is 0, this, let's say mu1 class, and 1 is mu2, right? 0 and 1, right? Right, and variance 2 and 3, yeah. So the variance is 2, is 3, right? So in some sense this is square root 2 is the standard deviation, right? So so that means so with some confidence you can tell that okay, the data points are lying within this minus square root 2 and to square root 2, right? What is square root 2? Around 1.41 or 4 something, right? So let's say from here, okay, I'll just use something. Okay, yeah, so let's say this is something like 1.414. So between here and this is 1 and this is minus 1.414. So these are the places where I can find class 1 data points, okay, with some confidence of course. And then you have this square root 3, right? This is 1.7, I guess 3, something like that. So again did this, let's say this 2, and this is around 3, so 2.73, something like this. So this is here, and minus 0.73, so something like this here, right? So this is the region of getting, sorry, this is the region for getting class 2 data points, right? So if you think about it, to solve it in a LDA format, like this, there's significant overlap that is present here, right? So if you see here, you have like a significant overlap, this particular region of the data. So for a LDA, for an LDA to work, actually this will be very difficult for it to be able to separate these two classes, class 1 and class 2, right? But whereas in question 8, if you see 0 and 5 and variance is just 1 and 2, so so 0, and let's take this 1, 2, so 0 is one class mean, mu1, mu2, right? Variance was what? 1 and 2, right? Okay, so 1 is basically from minus 1 to 1, and 2 would be like 1 minus 1 point, so something like 3.6 something here, and 6.4, something in this range, right? So if you see, you don't have much overlap here, right? So an LDA may be able to do perfectly, and we are saying may because this variance will not tell you exactly that this is the range of the data that will ever come, right? For example, I can have a data point which is lying here, which is from actually class 2, right? Which is from class 2, but just because it's an outlier, it has it's likely that, I mean, it has pushed the variance value to like whatever 2 here in this case, right? So it's possible, so it's possible that it's more probable that I can use an LDA to classify data points in this case, right? So does that make sense? Who was this question? Yeah.
Okay, sir.
Okay. Okay, good enough. So remaining questions. So okay, let's just go through one by one. So for example, for linear classification, we use linear function to separate the classes, right? This is the idea in linear classification. modeling, so the data modeling can be any complex function that you want. The idea is that when separating, you want a linear function. That's the idea of linear classification. Oh yeah, I saw this question somebody raised. So logit transformation for given data is, so the answer is 4 by 3. Again, it's a very straightforward thing which is there in the class, by the way. So logit transformation, so this is question. So logit transformation of any probability is just p by 1 minus p, right? So probability of x equal to 1 here is, I think, 4 by 7. 1 2 3 4, yeah, so 4 by 7. Obviously it's an estimate, so 4 by 7. So logit would be, logit of this value is going to be 4 by 7 by 3 by 7, so just 4 by 3. Yeah, so logit range is what actually, by the way? Anybody want to tell me what's the range of values that logit function can generate? So if I were to draw logit as a function from something to something, what is the range of logit function?
0 to 1.
Sorry?
0 to 1.
No, see, we just got, no? So range I'm asking. So, okay. So logit takes a probability as the input. So obviously 0, 1 becomes the domain of the function. So what is the values that logit can generate?
0 to infinity.
0 to infinity, right? Because if you, very simply, if you see here, if p is 0, logit becomes 0, right? And if p is 1, logit tends to infinity. Yeah, so as p tends to 1, logit tends to infinity. So this is the range that logit will generate, right? And if logit equals to exactly 1, what happens is we say p is equal to 0.5, right? So when you have complete uncertainty, like for example, if you have two alternatives and you have p is equal to 0.5, so you have like no inkling whether it's on this side or the other side, at that time logit is equal to 1. Anyway, so that's logit function. Output of binary class logistic regression lies in the range. What would this be? 0, 1, right? Because then your the binary class logistic regression is just outputting the probability of any class, of any data point belonging to a particular class, right? So the probability is always between 0 and 1, right? So that's the question number 3. Question number 4, it's a bit of an algebra. So I think it's 1 minus, right? 1 minus p of x, okay. P of x by 1 plus p of x is beta naught plus beta x, right? So this means that 1 minus p of x by 1 plus p of x will just be e power beta naught plus beta x, and using simple rule of ratios and proportions, this is divided by 1, so you can do a minus b by a plus b. So this becomes 2 times p of x by 2 is equal to 1 minus e power beta naught plus beta x by 1 plus e power beta naught plus beta x, right? So this is the answer. This is p of x. All right. Logistic regression is robust to outliers, and the reason is that your smashing of output values between 0 and 1 dampens the effects of outliers, right? Linear models are robust to outliers. This is wrong, right? Because we know very clearly when you want to take sort of MSE sort of a thing, where you take like a mean square error, right? So what will happen is if something is an outlier, the error for that particular prediction will be very high, and therefore that will start dominating the term of the mean square errors, right? Then the parameters in logistic regression tend to take small values due to nature of problem setting. So this is not right, because we don't put any extra constraints over the parameters that the function can take in this particular problem space, right? Okay, this is something altogether. So this is the idea, right? Good enough. So then 6, what is the aim of LDA? Straightforward. So this, you want to minimize the intra-class variability and maximize the distance between the two mean of the two classes, and this is what gives rise to the alternate formulation of LDA, right? So in the class, sir showed that one way to arrive at LDA is to assume the Gaussian assumption on the class conditional densities, right? The other way is you want to just look at you have a function which try to minimize this sort of a quantity, right? To this question number 6, yeah, right? You had this mean m1 minus m2 squared, and then divide by, so this is the mean between class variability, right? And within class variability you had some complicated thing, right? Some x, I guess s, something extra, something that we had. So all of this, so this, when you try to minimize, you get your another form of LDA. All right. Good. So 7, 8, and 9 we discussed, and 10, yeah. So LDA assumes the class data to be distributed as Gaussian, as we discussed just now, right? Okay. We'll move on to practice session of week 3. Yeah. First question. Anyone who wants to answer this? Have you all tried the practice sessions, practice questions? No takers, eh? All right. So the first question answer is basically your forward stage-wise selection, right? Because in forward stage-wise, the idea is that you will use your regression coefficients to be whatever you got the regression, you got the value by regressing the variable and the residual coming up until that particular point of time, right? So those particular coefficients can change when you were if you were going to apply the same set of subset of features directly on a linear regression, right? And this is a property of the forward stage-wise selection. So we know that it happens, but we still go ahead with doing it because it basically saves time in when you have large number of features present, right? Okay, so question 2, any ideas? Anybody tried doing this? So by the way, principal components, how do you find principal components? What is principal component, by the way? Anybody? It's a chat, is it?
Sir, I could not. Please tell me about this PCA, sir. I have doubts, sir. I could not understand by the lectures in the video
Okay.
lecture.
Okay, all right. So we'll take a short prelude in PCA. So in PCA, the idea is that you're trying to so the main basic assumption of PCA is that your information measure, or in some sense that information is can be quantified by variance in the data, right? So the idea is that you want to maximize your information, so you want to find out some directions which maximize your variance. Okay, this is the core question of PCA. So if you go ahead and plug in the math for all of this and try to solve this, so what happens is you end up getting the directions which are basically your eigenvectors. But eigenvectors of what? Eigenvectors of the covariance matrix. Right? And obviously it's a sample covariance matrix. Alright. So for example, that is, let's say you have X, which is for example number of samples cross number of features data set. Does anyone know how to calculate the covariance matrix from here? Given this data, how do you calculate the covariance matrix of X, covariance matrix of this data? No. So ideally, what you need to do first is basically you need to mean center the data, right? What does this mean, by the way, mean centering the data? Any idea what mean centering means? So let's say you have samples, right? Xi, which belong to R power n, right? So n is the number of features here. You calculate the sample mean, mu. Let's say capital N is the number of samples that you have, okay? So I equal to 1 to capital N, yeah, so Xi, yeah. So this is the sample mean, where N is the number of samples. What you do is now you transform this Xi to Xi minus mu, okay? All right, and now this becomes your mean centered data, right? So in this case, what will happen is when you have X in this format, n cross n sort of thing, your mean is going to be a vector of the size n cross 1, right? So then you basically take your mean across rows for each column, right? You'll get your mean, you'll get a sample mean mu, you subtract them from all the rows here, you'll get some X bar, let's say. Yeah, so this will be again an n cross n matrix, but with all your columns having 0 mean, yeah, after subtraction. So columns have 0 mean. Now post this, what you do is once you have this, you can take X transpose X bar. This will be a covariance matrix, sample covariance matrix. All right, X transpose X. And this is because you can basically just see this as I equal to 1 to n Xi minus mu trans Xi minus mu transpose. Okay, this is how you get your sample covariance. All right, so once you have the covariance matrix, you get your eigenvectors from this. So the idea is that maximum eigenvalue, okay, would correspond to the eigenvector. So the corresponding eigenvector to this maximum eigenvalue would correspond to the eigenvector which gives the maximum direction projection. Okay, and so on. So if it is the second max eigenvalue, you get the second most important principal component. So principal components are basically eigenvectors. All right, so this is the basic short way of talking about principal components. So for example, if you want to solve this using your numpy, right, so you can take so you have your numpy here, and this is the data that you have, right? The data that you have, all of these. So you have 5 samples, right? You have 5 samples and three features for each sample, and then you take your mean. So mean is going to be a 3 cross 1 vector, right? And then you subtract your mean from the data. So this is your mean centered data. All right, Your covariance matrix is basically just your matrix multiplication of x transpose and x. Obviously, so it will be a 3 cross 3 matrix, right? Because so covariance matrix is between features and features. So you're talking about from between two features, what is the variance among them, right? Using the data as your true way of looking at it. And then you can use this function, eigen function, to generate your eigenvectors from this particular covariance matrix, right? So you get your eigenvalues here and eigenvectors here, which you can see plotted, right? So basically eigenvalue of 95, so that means that this is the highest, this is the first principal component in some sense, right? Then you have 4.9, then 0.5. So this is your first principal component, this second principal component, and the third principal component. Okay, so we have this data until now. So if you see, this will not match your options anywhere, by the way, right? But one property of eigenvectors is that, so eigenvectors are not just one vector though, right? They're directions. So for example, let's say if ax equal to lambda x, I can always multiply some k into this, and I can write a into kx equal to lambda into kx, right? So this k is also this kx is also an eigenvector of a with lambda as its eigenvalue, right? So in this case, if you see, the NumPy solver gave us a eigenvector like this, right? So if I multiply this with -1, I basically get the answer here, right? So minus 0.31 and minus 0.8 and minus 0.5. Okay, so this is the answer for the second question. Third question is basically talking about for this given data, find the transformed input. So to find the transformed input, what you do is you take the eigenvectors which are the most important. So they are told here you want along the first two principal components, right? So here this is the first principal component, this is the second one, right? Based on how their eigenvalues are. So these are the first two principal components, and then you can basically do your matrix multiplication of this chosen eigenvectors, chosen principal components, and your x that you had generated that you had before, right? So that you can use to get your transformed input. Okay, so in this case also you might find that there's a sign mismatch, which makes sense because your eigenvectors can be any scaled value. So just take that and you can find out your best answer for this. Yeah, so that's about it. Okay, any questions in these two questions, question 2 and 3?
Sir, Raz, I have one doubt.
Yeah.
This is the mathematical things we are doing. Okay, this okay. But in the practical things, how can I know that I should apply PCA and IDA? I have the confusion on that. Could you please explain the things?
Okay, so you have doubt within applying PCA or which is the one?
If I have one data set, so how could I know that I should apply PCA?
Okay. So what is the idea of applying PCA, by the way?
To maximize the information.
Maximize the information, correct. But a bigger idea of PCA is that you want to reduce your features.
Okay.
Right?
I forgot that point.
So for example, let's say you have like a 10k features for your data set. Now what happens is your PCA is going to give you some number of principal components, right? Now the thing is, what you will do is you can basically do one way of choosing how many principal components you want is by looking at the how much amount of variance is explained by these PCs, right? So let's say PC1, that is your first principal component, explains the amount of variance which is equal to the eigenvalue corresponding to this particular principal component, right? So let's say I'll name it as, let's say lambda 1, right? So PC2 will have lambda 2 and so on. Okay, so what you can do is you can look at some kind of a threshold. So you can say, so I will choose k, the first k principal components, okay, such that the summation of these lambda i's, I equal to 1 to k, right, is some threshold, right? It is greater than some sorry, less than, yeah. So it chooses yeah, so for example, let's say 80% or 90% or whatever. 90% seems better, yeah, right? So I'll keep on choosing the principal components based on, how much amount of variance do they explain, right? Now, by doing this so you have obtained k principal components, right? So now what will happen is your features from this 10k will reduce to, okay, this k is, okay, 10,000, let's say. So from 10,000 it will just reduce to k, right? And that's exactly what we're doing here. If you see here, now what has happened is I've represented each of my samples. So I had 5 samples, right? So each of the samples now have only 2 features, and I will use only these 2 features to work with my whatever ML algorithm that I want to apply, right? So this is the major use of your PCA algorithm in some sense, right? So you can reduce to the features to some low dimensional data and then apply your ML algorithm, right? Because you know that high dimensions can cause problems for your ML system to find out minimas and stuff. Yeah, go ahead.
Thank you, Raj. Thank you. Well,
Yeah.
good.
Okay, good enough. Yeah, so this is one thing. The other thing is, for example, what you could do, there's another use of PCS is that you want to visualize the data in the first place, right? So what you do is you just look at, first 2 principal components or maximum first 3 principal components, because we can't visualize post 3. So what you do is you just break it down into 2 and 3 and look 2 or 3, and then look at the data, how it's getting distributed in that particular space, right? So it's a PC space basically, right? And then look at the data here, and this can sometimes gives you good insights as to how the data is, and is there some sort of separability or not, and stuff like that. Okay, so that's the one way of using PCA. Yeah. Okay, any other questions on PCA or these questions 2 and 3? No? All right. So then, yeah. So then this question number 4 is basically you have 6 classes, but you have you've been given only 2 an algorithm which can use only 2 classes at a time, right? So one way to do is basically your 1 versus 1 approach. So where you choose 2 classes at a time to solve a problem, to train a ML classifier, and then you finally choose based on some voting mechanism, right? So here you'll basically have 6C2 sort of number of classifiers that you need to train, right? So this will come down to 15 would be your answer. All right. Yeah, so with respect to discriminant analysis, which of the following is true, consider 2 class case. Anybody want to try this question? Which of these 3 are right? all of them are assuming this, covariance matrices are spherical and equal, which is a very good thing. After that, what would be your, I mean, what any guesses as to what the answer could be? No. Okay, so the question number 5. So here the idea is that so what is your boundary between any 2 classes, right? So you have it like this, if I'm not wrong: log pi k by pi l minus half mu k plus mu l transpose sigma inverse mu k minus mu l plus x transpose sigma inverse mu k minus mu l equal to 0. So the set it is covariance matrices are spherical, right, and equal. An equal assumption in a part of LDA work. Okay, so if it is spherical, so when is sigma spherical? So what is the form that makes that sigma is spherical? Any idea?
No idea.
All right. So sigma spherical would basically mean that it is something like this. It's like lambda into I, right? So that is, so if you see here, so why does it make sense, right? So spherical means that it's the same amount of spread in all your directions. Okay, so which is given by this lambda. Okay, and spherical happens when you have no other interactions between any two variables, right? So therefore, so all of these all of the diagonal elements except that, everything will be zero, right? So so sigma is of this form, which is it's a lambda I sort of a matrix, right? So if you were to substitute that here, actually let me not use lambda because we use it for many other reasons. So I'll just do something like Si. Okay, so S is the variance of each particular dimension here. All right, so if you use that here and substitute that here, what you will finally get is something like this: X transpose mu k minus mu L is equal to half times mu k plus mu L transpose mu k minus mu L minus S times log pi k by pi L. Yeah, where k and L are the two classes we are considering, and pi k and pi L are your priors, mu k and mu L are means. Anyway, all that is clear from the formulation. Okay, so once we have this, any ideas how to proceed from here? So what is the question, right? So when both are spherical and equal, the decision boundary will be the perpendicular bisector of the line joining the means. Again, same thing. So here the thing is, will it be perpendicular? And the third thing is saying that if the priors are equal, then it will be perpendicular bisector, right? So a very subtle difference between 1 and 3, which is that you're imposing a condition on the priors also, right? Okay, so if that's the case, so okay, with this, then any thought process as to how to proceed from here? So you have, so this is the hyperplane that is basically separating the two classes, right? Separating two classes hyperplane, right? So if you have to prove that this is perpendicular to the line joining the means, how would you go about doing that? So let's say this is just hyperplane. Okay, this is the equation that we saw previously. Now let's say if I take any 2 points here, I'll name them A and B. Okay, so if the line joining this A and B, okay, if this is perpendicular to the line joining the means, so let's say this is the some means are here, and this is 90 degrees, let's say mu k and mu L, right? So if this happens, then I can say that this hyperplane is perpendicular to the line joining the means, right? So if the points A and B are lying on this hyperplane, and let me do one thing. Let me just give this as some h, right? So this whole quantity is h. So if they're lying on the hyperplane, what that means is that A transpose mu k minus mu L is h, and B transpose mu k minus mu L is also h, right? Because they satisfy the equation, right? And hence they are lying on the hyperplane. So the line joining A and B is just A minus B, right? So what I need to prove is that mu k minus mu L transpose A minus B, right, has to be 0. That is the dot product joining the lines A and B, and the two means are 0, right? So what I can do now is I can just write mu k minus mu L transpose A minus mu k minus mu L transpose B, right? This is this particular thing. This is h, this is also h, so this is 0, right? I hope you understand that this is equal to mu k minus mu L transpose A. It's the same thing here, right? Okay, so this proves that they are perpendicular, right? So and see, this is for any 2 points lying on the hyperplane, right? So for any 2 points, A and B, right? So hence this makes sense. Okay, so with this, so therefore, so we know that it is going to be perpendicular, but the idea is that you want to check will it pass to the bisector or not, right? And you can check that here. For example, let's say if pi k and pi l are equal, this term becomes 0, right? So the point half of mu k plus mu l, that point lies on this hyperplane, right? Because it will satisfy this equation. Okay, so only when, right? So only when pi k is equal to pi l, right? What happens is half of mu k plus mu l, which is the midpoint of the line joining mu k and mu l, lies on the hyperplane, right? Because it ends up satisfying this equation, right? So hence, only if it is so, it will be a perpendicular bisector also. Okay, here we have proven that it is perpendicular. All right, cool. Any doubts in this? Dots. All right, so this is your week 3. Week 2, any questions that you have that you want me to solve? So week 2 question 1 is straightforward. We don't have any constraints on the parameters, so they can take any value in the real space. Question 2 is about understanding what does this correlation coefficient mean, right? So when it is close to 0, it tells that if you regress y on x1, it won't explain away y, right? This is the idea of this the coefficients that we have in the linear regression. Consider 5 10 examples, right? So this is again a very straightforward thing. What you can do is for each of these a and b combinations, you can find out what f of x would be, subtract f of x and y, square it, and then take the mean across all the data points, right? So that will give you a mean squared error as a loss. Whichever combination is giving you the least, that will be your chosen a and b combinations. All right. Fourth question is about what happens if she studies for 4 hours. So see, h is basically your, so if the person studies by 4 hours, it will go up by 60.8 points, right? So we're not saying what will be the final grade here. The question is how much it will go up by, right? So the difference will be whatever is a factor of this particular h, right? So it will be h into this guy. So 4 into this is 60.8 points. All right. Again, this is very straightforward. Much of it is covered in the I think shrinkage methods, right? So ridge has no sparsity constraint and lasso has a sparsity constraint. All right. Yeah, and lasso will choose them randomly if they're collinear variables, right? Orthogonalization is also covered clearly here. So basically, it will make sure that you can use you can get each of these coefficients in a univariate regression method, right? Again, question 7 is about the actual definitions of these methods. So stepwise is actually this, right? So variables are added one by one to produce the best fit line till then. And in forward stage wise, what you do is you basically start looking at the residuals and choose variables based on which have the maximum correlation with the residual. And this is a standard thing of the regression model. That is your x transpose x theta, that is theta is your weights, will be equal to x transpose y. All right. And any questions here? Do we have people? Okay. Any questions here? No. Okay. All right. So practice week 2 questions. Okay, so we covered the first part in the linear algebra, I think the second week that I had taken, and we just go ahead and look at that once. Stochastic matrix. So okay, people have idea how to solve question number 2 here. So this is week 2 practice 1, right? Question 2, anybody? So this is a bit tricky, at least in my sense. So so if you have a stochastic matrix, a row stochastic matrix, what that means is your row sums are 1. All right, so row sums are 1. Now so when that happens, all right, so let's say you have a matrix A. One second. Yeah, so let's say you have a matrix A, some A11 until A, this is M cross N, so A1N, AM1 to AMN elements, right? So this sum is 1 and so on, right? Each row sum is 1. So what is the one eigenvalue that you know for sure exists in such matrices? Eigenvector, sorry. So imagine I take a vector x, let's just call it as 1 bar, which is all ones. Yeah, so x will actually so okay, one second, this has to be a square matrix, no? All right, yeah, so square matrix n cross m. Yeah, so I have here n cross 1 vector, which is all ones, right? So if I take this a into 1 bar, what will a into 1 bar be? Right, so what are we doing here, right? So yeah, I'm multiplying all of this with ones. So if you take this product and this your standard matrix multiplication method, so what I'm doing is I'm doing a11 plus a12 plus so on until a1n, right? Which I know for a fact is 1, right? Because the row sum is 1, and same thing will happen for all the rows, right? So what happened? So I'm getting 1 into 1 bar again, right? So there is a vector of all ones, which is actually an eigenvector of A with the eigenvalue 1, right? So any row stochastic matrix will have one of its eigenvalues as 1, right? So if you do that way, you can eliminate options B, 1 and D, 1 and 4, right? Because the saying is strictly more than 1, strictly less than 1 and stuff like that, right? Now to know whether it is less than or equal to 1 or greater than or equal to 1, I'll just give a hint and we'll move ahead from here. So the idea is that I can write ax equal to lambda x, right? Now from here, to move forward is I can say, okay, so see the thing is, so let's say so x is a vector, right, which is x1 to xn. Let's say x, so k is the index such that x k mod is the highest, right? The maximum absolute value index. Okay, now we know for a fact that this has to be greater than 0. Why should this hold? Because x vector as such cannot be a 0 vector, right? There should be some non-zero value here, right? It can be positive, negative, that doesn't matter, right? So I will have at least one element xk such that its modulus is more than 0. That's compulsory, right? Now with this in mind, what we can do is choose one row here and one row here, right? Let's say the ith row or whatever. So if I choose ith row here, it's like looking at this quantity, right? This is just going to multiply ain xn, and it will be equal to lambda times xi. Okay, so now I'll point you to the idea that what you could do here is look at modulus of lambda x k. Okay, look at this quantity, expand the rows here. What you'll end up proving is that this has to be less than or equal to xk. Okay, and since xk is non-zero, I mean more than 0, what will end up happening is you'll end up proving that lambda, or in the question b, is less than or equal to 1. Okay, so it's a simple thing. Just expand this particular this particular expansion and apply something like triangle inequality, etc., which govern this modulus operator, how it works, right? You just need to know this, you'll be able to come to this answer. Yeah, all right. Question 4 again is straightforward. The first 3 questions are straightforward. The fourth thing, non-zero eigenvalues. So this is also a bit tricky. Question 4. Yeah. So what you need to think is, you need to understand A transpose AX equal to lambda x, let's say. Okay. We're saying that let's say if lambda is not 0, and we know for a fact x is not 0, right? So this quantity is non-zero. If this quantity is non-zero, A into A transpose x is something which is non-zero. Now this will never happen if A transpose x is 0. So this implies that A transpose x is not 0. And this is important because what ends up happening is, and this sort of we solved in the last time, you multiply A transpose x here, this becomes your new y, right? We need to prove that y is not 0. So you will do that using this approach. All right. Okay, we're running out of time, so I'll just go ahead. Question number 5, again same sort of approach you can apply. Try each of these A and B's and find out what is the loss, and then choose which is the best one, right? 5 training instances. So this again straightforward. You can just look at the distances for each of these points from your 3,6 point, right? And you'll find out y and and see here k's are different. So for this you get I guess 2.5, and for this you get I guess 2.3 or something. Then you have bias and variance chart here. So this is a very classic example, by the way, for trying to understand what bias and variance could means here. So these two, player 2 and player 3, have low bias, right? Because of the fact that they don't have much variability. Low variance because low bias because they're close to the center, which is where you want to go there, and 1 and 2 have high variance because you can see that there is a lot more variability in the way they are playing, whereas 3 and 4 are not variable. I mean, have less variance, but and player 4 has high bias because it's missing the center dot by too much compared to player 3 and player 1, right? All right, so this is this one. Yeah, question 8. Again, some thought process, you'll be able to understand that it's I think option 2 and 4. So when you have small data set, see the data itself. So when you have small data set, so choosing low variance classifiers is better, because when you have small data set, you're already going to have like a high variance in the data, right? Because you cannot estimate the variance very good. So hence choosing high bias low variance classifiers would be better, and with large data set you can have a low bias and high variance classifier. All right. Yeah, so question 9 is also a good question. Okay, all right, so we'll just move ahead for now. Any questions here? Any doubts? All right. So week 1 quiz is actually yeah, a lot of this is just trying to understand when you would apply unsupervised learning and supervised learning, etc. And these are again straightforward stuff here. So by the way, what is 0-1 loss? Any idea what is 0-1 loss? No idea. So 0-1 loss basically tells you that, for example, let's say your prediction matches your data, right? Your training testing example. If it matches, then there is no loss, that is 0. And if it doesn't match, you take a constant loss of 1. Okay, so so that's the meaning of 0 1 loss. So you can just look at wherever it doesn't match, you'll put as 1. If it matches, you'll put it as 0, and that mean will be your mean of 0 1 loss for the given data set. All right. Again, this is straightforward from your videos from sir, and again this is also straightforward from sir. All right. Week 1 practice. So here, if you think about it, detecting fraudulent credit card transactions through clustering is the best approach, right? See, predicting the amount of rainfall based on various cues, so that's like a problem of regression, and training a robot to solve a maze is like your RL problem, reinforcement learning. So why does this help in why to do clustering here is because you can look at, see, people who are non-fraudulent will behave in one certain way, right? For example, they'll have like a very similar sort of what do you call that, purchasing patterns and stuff like that, right? So they won't purchase once in a lifetime with a high high value at once and stuff like that. Whereas in fraudulent cases, you will have very very specific patterns of cheating and stuff like that. So you can actually find those out using clustering, right? So that's the idea behind using clustering for doing this kind of a problem. We discussed, I guess, these two in the previous classes, and so this was a bit straightforward. You just need to apply the binomial distribution a bit carefully, you'll be able to get there. All right. Okay, almost there. So I'd like to do this quiz of the practice session of this week 4. Let's do it next session. All right, so we'll dig deep into how to find out convex functions using Hessian matrices, and this problem of optimization here. Right, so how do you do that? How do you use a Lagrangian? How do you use KKT conditions and stuff like that to apply to get to the solving these kind of problems, right? And these become important in your support vector machine formulations. All right, so this is all about it. Any general questions you have? Before we
Actually,
close?
I have missed the section assignment 3. Is it possible to reattend the same with other questions?
Okay, so yeah, I'll ask the course TAs. I think so I'll ask them and let you know what can be done.
Actually, I am forget the date. Actually, I am think it is 18, but it is last date is 17, so that I made the assignment.
Uh-huh.
If possible, then some other question given me so that I can attempt the same.
Sure. So I'll ask them out what approach they have to
Yeah.
solve this kind of a issue. Yeah. So they'll get back to you.
Thank you very much. Thank
Yeah.
you very much, sir, for this session. Thank you, sir.
Sure. Yeah.
Wonderful session.
Thank you. Any other doubts? General doubts? Anything? No. All right then. So we'll stop the session right now. So next session will be again in same time, 4 to 5. Next week we'll mostly deal with SVMs and a bit of kernels and some intuition about why kernels help and how do they work and stuff like that. All right. Okay. See you guys next week. Thank you.